So welcome back again. So now we have a seminar, and our speaker is Professor Daniel Grumiller from Vienna, and he will talk about general two-dimensional dilaton, I don't know how you say, dilaton gravity, so which is connected to gravity in lower dimensions, as I explained. So this is a connection with my lecture, and Daniel has made consistent key contributions to lower dimensional gravity, in particular to dilaton gravity. So it's a great pleasure to have him here for this first seminar of the course. So Daniel, the floor is yours.
Thanks, Marc. Yeah, thanks for the introduction and also for the invitation. It's a pleasure to be here. And I'm going to talk about general two-dimensional dilaton gravity. And I organized the organization of this talk in terms of questions. So I'll start with the question why. Why do we study these theories in the first place? Why specifically 1 + 1 dimensions? Then I'm going to cover which theory we should study. As Marc explained nicely already in his talk, we cannot use Einstein gravity in 1 + 1 dimensions. And then most of the talk is concerned with how. How do we study these theories? In particular, how do we solve them? How do we find solutions to the classical equations of motion, which then gives us information about the asymptotic structure of space-time, which is one of the main themes of Marc's lecture series and also a topic that I'll cover in my talk today. And okay, the lower two questions are maybe not readable in the lower rows, but I read them here. So the fourth question is, what about asymptotic structure? So that's also a key element of this talk here. And then finally, I'll give an outlook. Where do we go? What can we do with these results? How can we lift them perhaps to higher dimensions? Or what lessons can we learn for general aspects of classical and quantum gravity and holography? Okay, and if at any point you have questions, just feel free to interrupt me. Our goal is to finish in 1.5 hours. I'll stick to this, but I don't mind skipping some parts if you have more questions on the earlier part. So don't feel embarrassed and just interrupt me and ask questions. Okay, so the main answer to the question why study gravity in 1 + 1 dimensions is very simple, namely simplicity. 1 + 1 dimensional gravity is very simple. So you might ask, well, okay, if 1 + 1 dimensions is so simple, why not go even lower in dimensions? Why not study gravity in 1 + 0 dimensions, or 0 + 1 dimensions, or 0 + 0 dimensions? Well, the answer is that we want to keep some structures that make it worthwhile to study such theories. So in particular, we want to have one time and one space dimension, simply because that means we have light cones, and if we have light cones, we can have black holes, and black holes are our main object of interest here. So one of the reasons why we consider not lower dimensions than 1 + 1 is because of our interest in black holes. So we have light cones in 1 + 1 dimensions. So that's one motivation. The second motivation is that if we want to build some toy model of gravity, then it's nice if it reflects some generic features of gravity. And one of the features of gravity is that the gravitational force is described in terms of curvature of space-time. So we should make sure that our model still reflects that, so that there is actually curvature. And if you go down to 1 dimensions or lower, there is no intrinsic remaining curvature. So 2 dimension is the lowest dimension where you have non-trivial Riemann tensor. And as Marc explained in his lectures, in 2 dimensions, the Riemann tensor is actually determined uniquely by the Ricci scalar. So there's only one algebraically independent component in the whole Riemann tensor, but at least there's one. So it's not 0, you still have curvature, and all the curvature information is captured already by the Ricci scalar. And that's a simple way to see why gravity in 1 + 1 dimension is simpler, just because there's far less bookkeeping you have to do. There's only one component in the Riemann tensor. Okay, another reason why 1 + 1 dimension is the lowest dimension for many considerations is it's the lowest dimension where the boundary still has a non-trivial dynamics, or a non-trivial dimension. So it's the lowest dimension with boundary dynamics. And I'll explain in more detail what I mean by this. But roughly speaking, if you have some two-dimensional space-time, let me draw a so-called Penrose diagram. In this case of some black hole in two-dimensional anti-de Sitter space. Then this is the boundary, and it still has one direction, in this case time. So in case you haven't seen these diagrams, these are the famous Penrose diagrams. And this particular one is a Penrose diagram of an ADS2 black hole, so a black hole in two dimensions that is asymptotically anti-de Sitter, which is a topic that I'm sure Marc will cover in more detail in later lectures. And well, if you've never seen these diagrams, the main thing you have to know is that light travels on angles of 45 degrees in these diagrams. So these diagrams faithfully depict the causal structure of space-time. So for instance, if you are at some point here, then you can communicate not just with this wiggly line here, which is the singularity of the black hole, but also with this straight line here, which is supposed to depict the asymptotic region. So one of the key technical aspects of Penrose diagrams is that they map infinity to some finite region. So distances are not faithfully represented, but the causal structure is. So if you have some observer that is very far away from the black hole, that observer will move on some world line close to this asymptotic boundary. And if you are here, then you can send signals to that observer. But if you are beyond this dashed region, then no matter what you do, your signals inevitably will end up in this singularity, and you cannot communicate with this infinitely far region. So then you're trapped in this dashed region, and that dashed region here, so the region beyond the dashed lines, is the black hole region. All right, so again, 2 is the lowest dimensions where we can have such structures. So what this provides us with is manageable time models for black hole evaporation, for holography. I'll explain what I mean by this in more detail, and also for quantum gravity. So the last point is one of the main motivations why these 1+1 dimension models have been studied. There's a lot that we don't know about quantum gravity, and many of the issues related to quantum gravity are of conceptual nature. So for instance, the information loss problem, the question how black hole evaporation can be reconciled with unitarity of quantum mechanics. And these questions are conceptually independent from the dimension, and therefore it's interesting to solve them in a model that is as simple as possible, because the hope is that this gives some conceptual insights or breakthrough that then you can generalize or apply to more realistic or more complicated systems. So one of the slogans you can take away from this motivational part is that the focus is on solving conceptual problems and avoiding technical problems. And by going to 1+1 dimensions, you minimize the amount of technical problems. So we want to solve conceptual problems and avoid technical problems. And if that slogan is still too technical for you, a more colloquial version of that slogan is that we're looking for the hydrogen atom of quantum gravity. So what do I mean by this? Well, the hydrogen atom is not the most important atom for chemistry. Its chemistry is rather boring as compared to more interesting atoms. But undoubtedly, understanding the quantum mechanics of the hydrogen atom was a big conceptual breakthrough in our way to understand quantum mechanics. And this is essentially the same philosophy here. Of course, black holes in 1+1 dimensions will not be relevant for amazing pictures like the one that we will probably see tomorrow by the EHT collaboration at 3 p.m. But they might help us to understand quantum gravity and to resolve some of the conceptual problems. Okay, there are also some caveats that I want to mention. So there are some instances where going down to 1 + 1 dimensions might not be suitable for your purposes. The first one is that there are no gravitons in 1 + 1 dimensions. On shell, it's already true in 2 + 1 dimensions. So if you just consider Einstein gravity in 2 + 1 dimensions, then there are no local excitations, no gravitational waves. But at least off shell, you do have modes that you can associate with gravitons in 3 dimensions. And in some models of gravity in 3 dimensions, you can excite those modes. You get, for instance, massive graviton excitations. But in 1 + 1 dimensions, no matter what you do, you can never have gravitons. Any 2-dimensional metric can be split into a pure gauge part and a trace part, but there's no transverse traceless piece. So if your goal is to understand gravitons, then you shouldn't go down to 1 + 1 dimensions. However, most of the aspects of gravitons can be understood by linearizing gravity, and linearizing gravity is something we can do in 4 dimensions, and the resulting equations are essentially equivalent to the Maxwell equations, which we understand pretty well. So this is not a big downside. And the other caveat, which was already mentioned by Marc, is that there are no equations of motion that follow from the Einstein-Hilbert action in 2 dimensions, just because of this identity that Marc has shown to you. The rigid tensor in 2 dimensions as a kinematical identity is equivalent to 1/2 g mu times r, so the 2-dimensional Einstein tensor vanishes. And that's true for any metric. It doesn't have to solve any field equations, it's just a 2-dimensional identity. So this is an identity in 2 dimensions. There are different ways to see this. You can also just look at the Einstein-Hilbert action and realize that in 2 dimensions it's a total derivative term. So it's the kind of term that you would drop when you derive equations of motion. So there are no equations of motion from Einstein-Hilbert. So that just means you have to consider a different theory than Einstein-Hilbert. That's the second caveat. Okay, and that brings me to the second point, which theory to consider. If it's not Einstein gravity, what should we consider instead? And there are numerous paths that lead you to the same conclusion. I'll just briefly summarize them here. I'll not elaborate on them in great detail unless you want to ask questions. So one thing you can do a dimensional reduction to 2 dimensions. Say you start with Einstein gravity in d dimensions, you impose strict spherical symmetry at the level of the action, you integrate out the angular part, then you end up with an effective 1 + 1 dimensional theory. But that theory doesn't just contain the metric, it contains additional fields. Like in Kaluza-Klein reductions, it contains additional scalar field and possibly additional vector fields. Now, vector fields in 2 dimensions you can integrate out, essentially. They are topological. So you end up with a scalar tensor theory. So in addition to the metric, you have a scalar field. Marc called it phi. Well, I have different notations, so I call it x, but it's the same kind of scalar field that Marc wrote down. So that's one path. You just start with Einstein gravity and do dimensional reduction. The second path is you start with string theory. So you can consider string theory with 2-dimensional target space. And string theory by itself is a 2-dimensional theory. It's a sigma model. And the consistency condition of this sigma model, in particular conformal invariance, lead to conditions, the vanishing of the so-called beta functions, if you're familiar with this, then you know what I mean. If you're unfamiliar with this, just ignore the next minute. And the vanishing of these beta functions can be reinterpreted as equation of motion coming from some target space action. And if this target space is two-dimensional, you end up with a two-dimensional theory of gravity. And that two-dimensional theory of gravity has, again, the same field content, namely it has a two-dimensional metric. It has a Dilaton field. That's where the name comes from. So the scalar field here is called Dilaton field. And then there can be additional fields like a B field, which, again, you can integrate out. So again, you end up with a scalar tensor theory, which from now on I call Dilaton gravity. But Dilaton gravity and scalar tensor theory are synonyms. So it's, again, a theory in two dimension defined by a metric and a scalar field. Now, you might start right away from scalar tensor theories. So you can consider Jordan-Brown-Sticker theory. So if you just directly start with scalar tensor theory, of course, you end up with the same field content as well. And then there are two more paths to this. So you can consider theories known as Poincaré gauge theories. So these are theories where the Lagrangian is a function of curvature and scalar invariance constructed from torsion. And one can show that this is equivalent to such a scalar tensor theory. And actually, I prepared some exercises. So for those of you who are interested in doing this, one of the exercises is related to precisely showing this, the relation between Poincaré gauge theories, so theories that have Lagrangians depending on curvature and torsion, to these scalar tensor theories. And finally, much like in three dimension, there's a gauge theoretic formulation of three-dimensional Einstein gravity as a Chern-Simons theory. In two dimension, there's also a gauge theoretic formulation. So there's a gauge theoretic formulation intrinsically in 2D. And as we'll discuss in a bit, this gauge theoretic formulation is also equivalent to a scalar tensor theory. So all these approaches ultimately lead to the same theory, or the same class of theories, namely Dilaton gravity in two dimensions. Yes?
I missed the point why you get only one scalar field and not two constants.
This is true. So if you, it depends, of course, what kind of dimensional reduction you do. And you're right, you can get more than one. If that happens, then you just get, well, additional scalar fields. The scalar fields you add on top of the one that I call Dilaton, you can interpret just as additional meta degrees of freedom. So in the same way that you can add additional scalar fields to Einstein gravity, you can add additional scalar fields to Dilaton gravity. But those play conceptually a slightly different role. It's like adding matter to your system. So I will disregard this possibility, but of course it arises, for instance, in cylindrical reductions of Einstein gravity to two dimensions, you get additional scalar fields. I'm just focusing on the possibility of having at least one such scalar field. So we need at least one, and that one plays a special role that is different from the additional scalar fields that you may or may not have. And in particular, in the context of spherical reduction, it's true that you only get one scalar field. So that's why I focus on that case. Okay. Good. So let's start with the last option. I'll write down some gauge theory based on a specific non-abelian gauge algebra, namely on SL2R. And we'll see in a few minutes why. So, yeah, let's start with the last option. And consider an SL2R algebra. And, well, anticipating already the gravity interpretation, let me point out that SL2R is precisely the isometry algebra of two-dimensional de Sitter anti de Sitter space. So that's ultimately the geometric motivation why we're interested in this specific algebra. Okay, so what is the SL2 algebra in a convenient basis? PA are the translation generators, and in flat space they would commute, but in de Sitter, anti de Sitter, they commute into a cosmology constant term, so they don't commute. Instead, they give a generator of boosts on the right-hand side. This is, again, the epsilon symbol, and this is the cosmology constant. And the commutator between translation and boosts has the same form as in Poincaré, so it's epsilon AB times PB. So if you translate first and then you boost, and you boost first and then translate, the difference between these operations is another translation. And AB here, I have the range 0 and 1. Okay, so starting with this algebra, we can now define a non-abelian gauge connection, A, which lives in that algebra. And I'll split this connection already with respect to the components, PA and J. And I'm also using already suggestive notation. So I'll write down the connection one form as a one form that I call EA times PA plus omega times J. So the omega, the one form omega is related to a one form with two additional indices just by dualization with the Levi-Civita symbol. And this quantity is what is usually known as spin connection. And I'll explain in a second how it comes about. And this other quantity, EA, well, sometimes called dyad, I just refer to it as Zweibein. And I should say that I'm suppressing spacetime indices, so when I write something like EA, you should think about this as EA mu dx mu, and similar for omega. And what this quantity does is it basically puts you into an elevator frame. So this is the famous Cartan formulation of gravity, and this Vielbein, in two dimension called Zweibein, allows you to convert space-time vectors, so vectors that have a space-time index, into Minkowski vectors. So if you have an arbitrary vector v mu, you can contract it with this Zweibein, and in this way you generate a vector with an index A. And these Latin indices are raised and lowered by the Minkowski metric. So we have the Minkowski metric eta AB, and this is used to raise and lower these Latin indices, also known as anholonomic indices, or colloquially as flat indices. And it's convenient in two dimension to use light concoordinates, so for explicit calculations I use that eta plus minus is equal to 1. It's of course the same as the inverse, and the components eta plus plus and eta minus minus are 0. Yes?
Why do you have a cosmological constant in your commutation relations? Is it plus or minus 1? I mean, if you just have SL2R, normally there's no...
Sure, but you can, you can absorb it into rescaling your P generators if you want. Yeah, exactly. But that's why, I mean, so we want to cover both ADS and DS. So that's why I keep the sign here.
SL2R is SL2R.
That's true, but it's you can map, sure. But this basis is sort of adapted. I mean, it doesn't matter what the sign here is. You will always get SL2R.
Okay. You say that then I agree.
Yeah. As long as the sign is non-zero. I mean, if it's plus or minus, that's fine. Yeah. So, I mean, it's the the same difference as between SO2,1 and SO1,2, right? Those are the DS and ADS2 algebras.
Again, if you say yes. Yeah.
All right. So if you have this Zweibein, you can construct the metric in the following way. It's a bilinear in the Zweibein, E mu A, E mu B, eta AB. But you see that there's a redundancy in the description using the Zweibein. The metric has 3 independent components because it's a symmetric tensor, but the Zweibein has 4 independent components because it's a vector-valued vector, so it's a vector both with respect to the Minkowski metric and with respect to the spacetime metric. So it has 4 independent components, so there must be some local redundancy, and that local redundancy is an additional gauge symmetry. And that gauge symmetry is local Lorentz transformations, and the associated connection with this gauge symmetry is this spin connection. So that's why we need this additional quantity omega here. Okay, so that's the brief summary of the Cartan formulation. And now that we have this connection A, we can consider the non-abelian field strength, which is constructed in the usual way. It's dA plus 1/2 commutator A with A. And if we just insert and use this SL2 algebra, we get the following terms. We get d EA PA plus d omega times J. And then we get a commutator term involving the 2 P's. So we get minus 1/2 EA wedge EB lambda times epsilon AB times J. And then we get another commutator term involving PA and J. So we get another term plus epsilon AB EA wedge omega times PB. So this is the non-abelian field strength, now decomposed with respect to the SL2 algebra. Okay, and let me collect the terms in a suggestive way so that we can extract the geometric meaning of the various components of this two form. So I define the torsion two form TA as DEA plus epsilon AB omega wedge EB, and define the curvature two form as the omega, and the volume two form I define as 1/2 EA wedge EB times epsilon AB. So in light coordinates, this would be E minus wedge E plus in my conventions. So using these definitions, the non-abelian field strength is then just the torsion two form times the translation generator plus the curvature two form times the boost generator, and then minus this volume form times lambda times the boost generator. And having a two form is convenient to dimension because two forms you can naturally integrate, and we're interested in writing down an action. So any two-dimensional action should be the integral over some two form. So this is a natural candidate. The problem is that this still lives in this Lie algebra SL2. So in order to get rid of these generators, we have to introduce some additional structure. So the additional structure is provided by coadjoint scalar fields. Which I call B. And the action that I'm writing down is called BF action. And it depends functionally on this gauge connection A and on the scalar fields B. And it's given by kappa over, I think, 2 pi, yeah. And then the integral of an invariant bilinear form of this SL2. And then you have this inner product between B and F. So the Lagrangian of the BF theory is B times F, hence the name. You can interpret B as a background magnetic field if you want, but we're actually varying with respect to B. And F is the non-abelian field strength that we discussed here. So to be a bit more explicit about this bilinear form, one way to define it is that we introduce some dual bases and define the bilinear between J dual and J to be 1, and between P dual A and PB to be Kronecker delta AB. And these coadjoint scalars are then some scalar field X times J star plus a pair of scalar fields XA times P star A. So that's why I use the plural here, scalars. We don't just have one scalar field, we have an SL2R worth of scalar fields. So we have a scalar field X, which is not chosen incidentally. This will turn out to be our Dilaton field. And then we have additional auxiliary scalar fields XA, whose meaning I'll explain in a minute. Okay, so this is the action that we want to study. So this is a gauge theory, but it's a gauge theory that is likely to have some gravity interpretation because at least the fields contained in the connection do have a clear geometric interpretation in terms of Zweibein and spin connection. So I'll just insert now into my definitions and expand the result for this action, the BF term. And then I'll give this some geometric interpretation. So this expression BF is just given by x d omega. So that comes from, that comes from this expression together with this one here. Then we get, maybe I should use colors. Then we get that expression here. Yeah, let me keep this in white, actually. That's fine. Then we get this term in yellow with this term. So that gives us XA times the torsion 2 form. Oops. And then we get the last term, which is this volume form, which again goes together with this x term. So we get another contribution to the Lagrangian of the form minus epsilon times lambda times x. And now you see what happens when you vary with respect to xa. Variation with respect to xa establishes that Ta is equal to 0. And that condition is the condition of vanishing torsion. So the xa have an interpretation as Lagrange multipliers for the torsion constraint. So on shell, we get vanishing torsion. So in some sense, this is a bit like the Palatini formulation of Einstein gravity in 4 dimensions, where spin connection and Vielbein are independent variables. But when you vary the action with respect to the variables, you get field equations, some of which tell you that torsion has to vanish. So you can solve this for the spin connection, and then you find it's just a Levi-Civita connection, and you can convert your theory into a standard Riemannian theory, even though you started with a Cartan theory. And when we do this, so when we integrate out this Lagrange multipliers for torsion and express the spin connection in terms of the Zweibein, and then additionally use the relation between Zweibein and metric, we end up with a second order action that is equivalent, at least classically, to this BF theory. And that second order action depends now on the remaining field, so on the metric, and on the remaining scalar field that we haven't integrated out, so on X. And that's given by kappa over 4 pi. There's some extra factor 1/2. Then the volume form, d2x squared of minus g. And then we get the remaining term here, x times the curvature 2 form. So if I write in this way, this is just x times the Ricci scalar. And then the last term minus the volume form, so the volume form we have already, and then lambda times x. So we get minus 2 lambda times x. And that action was the first two-dimensional gravity theory that was considered in the literature and is known as the Chakif-Teitelbaum model. So I call this action JT. And it has a Lagrangian that is just given by x times r minus 2 lambda times x. So it's one of the simplest two-dimensional graviton models and the first one that was considered in the history. This is not the way how it was constructed, so the gauge theoretic formulation was uncovered a bit later. So Chakif and Teitelbaum started with the metric formulation. Okay, but I decided not to precisely follow the history, but to follow in a way that I hope is simple to understand. Yes?
So you have your gauge. I'm a little bit lost what the gauge transformations would be on your one form. Because the one form is sort of decomposed of the
Yeah, so we have SL2 gauge transformations, and so we have 3 independent gauge transformations. One of them just turns out to generate local Lorentz transformations. So there's one part of the gauge transformations that acts as follows. So delta lambda of omega is just d lambda, and delta lambda of E plus minus is, I guess, minus plus some factor lambda times E plus minus, something like that. And it acts trivially on the scalar field X, and it acts in the same way on this Lagrange multipliers for torsion. So one of the gauge symmetries generates Lorentz boosts. The other 2 generate gauge symmetries that at first glance look a bit weird. But then when you use the equations of motion, you can show that this just generates Lie variations of the field. So these remaining 2 gauge transformations generate on-shell diffeomorphisms. And that's actually one of the exercises to show precisely this. No, I'll come back to that exercise. And I know that they were distributed only before Marc's lecture, so I don't expect anyone to finish them. But yeah, so that's the meaning of the remaining 2 gauge symmetries. They correspond on-shell to gauge transformation. And by the way, the same happens in Chern-Simons theory. So in Chern-Simons theory, when you don't use U1, but I guess Marc is going to do this probably the next time, when you use SL2 plus SL2 gauge symmetry, or SO2,2, then you also find this feature that sort of half of the gauge symmetries in that case would correspond to local Lorentz transformation, and the other half on-shell correspond to diffeomorphisms. And the remaining ones, okay, I want to say this later, but since you asked, I can say it already now. So the relation between the gauge parameter that generates these gauge symmetries that on-shell correspond to diffeomorphisms and the diffeomorphism generator, which is just a vector field. So you make Lie variations along this vector field to generate diffeomorphisms. And the relation between these two is field dependent and involves this connection one form. So it's just a contraction of the vector field with the connection, and also the Lie algebra indices work out. So this generates diffeomorphisms on shell. And if you've never seen this, I recommend you to look at exercise number 3. And if you're stuck with that exercise, look at the hints on the back side. So I hope this is doable. And if you're still stuck, then send me an email at some later point. Okay. So this was historically the first model. And what we did in this work with 2 postdocs, so one current postdoc at TU Wien, formerly from Brussels, and another postdoc who originates from Brussels but is now at Perim Institute, Celine Zwickel. We studied the most general theory of two-dimensional gravity. And what is the most general theory of two-dimensional gravity in the second order formulation? So by most general, I mean up to the addition of matter fields. Of course, you can make the theory more complicated by adding arbitrary number of matter fields. So when I say most general, I mean given the field content of the metric and one scalar field. So what is this action? It's given by x times r minus curly v, and v is a function that depends on 2 arguments, namely on x and, well, in my conventions, on minus nabla x squared. So the special case of the Chakif-Teitelbaum model is where this function, and I guess I have a factor 2 here for convenience. So Vjt is just lambda times x. That's one simple model where this potential only depends on x and not on the kinetic term, and it depends on x linearly. But any such function leads to a legitimate two-dimensional Dilaton gravity theory. And our claim that I try to make a bit more precise is that this is the most general theory that you can write down.
So you will spell out the conditions?
I will spell out the conditions, in which sense this is the most general, what are the assumptions, and how you can actually prove this, yes. Well, that brings me to the third point, namely how. So now we know what we're aiming for. We're aiming for study of theories of that type. And how do we study them? Well, exactly like in 3 dimensions, and in the simple example of JT, gravity, it's useful to have a gauge theoretic formulation. Now, it's not at all obvious that any such model will have a gauge theoretic formulation, but it turns out to be true. And I want to present to you now this gauge theoretic formulation, which also shows that all these models can be treated on equal footing. And as we shall see, that's convenient because depending on how you choose V, you get geometries as solutions to these models with very different properties. You can get solutions with black holes with arbitrary number of Killing horizons. You can get solutions that are asymptotically de Sitter, anti-de Sitter, or flat space, or something else. So you can do a lot of toy model building by adapting your choices for this function V. And therefore, if we can say something that applies to all these models, that's very useful information. So the claim is that the gauge theoretic formulation of generic two-dimensional Dilaton gravity is given by a so-called Poisson-Sigma model. So I abbreviate this by PSM. So what is a Poisson-Sigma model? Well, maybe here let me add some references. So this was shown by Ikeda in '93. and independently a bit later by Schaller and Strobel in 1994. And the PSM action depends on some connections AI, some coadjoint scalars, which now I call xi, before this was the quantity I called b. And it's given by a generalization of the BF action that we considered. So it's given by xi dai plus 1/2 pij of xk, and then ai, sorry, I have to squeeze this in here, wedge aj. So this is, well, you see it's a two-form, dai, and it's contracted with xi, so that term is fine. And then we have ai, wedge aj, which is also two-form. And in order to contract these two indices, we need a two-index object. So this is this tensor pij. And this tensor has to obey the following properties. So pij is a Poisson tensor, which means, first of all, it's antisymmetric. Pij is minus pji. And it obeys nonlinear Jacobi identities. And they look as follows. So pil dl pjk plus the cyclic sum. So, okay, let me write it down. So pjl dl pki plus pkl dl pij. This has to vanish. So any tensor with these properties is a proper Poisson tensor, and you can use it to define a Poisson sigma model. So, yeah, let me show you some properties of these Poisson sigma models, and then let's recover as a special case the BF theory we considered initially, just to see you that this is a particular instance of these PSMs. And again, that's something that I relegated to one of the exercises to show the next statement. So the claim is that any Poisson sigma model has the following gauge symmetries. Delta lambda of AI is d lambda I. So you have the usual abelian part of a gauge transformation, the one that was also present in Marc's talk in the John Summons theory. But then you have an additional term, di pjk, contracted with aj and lambda k. And I'll comment on this in a second. And delta lambda of xi is just given by the contraction of lambda j with the Poisson tensor pij. So what you can see here is that this expression here in general depends on the xi's. So that means in general you get nonlinear gauge symmetries. So these are in general nonlinear gauge symmetries. So it's not just that they are non-abelian, they are not even of Yang-Mills type in general. An exception is when the Poisson tensor is linear. In the xi. And maybe I should explain the name, why it's called Poisson sigma model. So, well, Poisson is hopefully clear because it's defined by the Poisson tensor, Pij, and sigma model because you can interpret the scalar fields xi as target space coordinates. So you have a target space manifold that is a Poisson manifold equipped with this Poisson tensor, and the xi's you can interpret as target space coordinates on that Poisson manifold. So that's a typical sigma model construction. You have a world sheet and you have a target space, And in our case, the target space is a Poisson manifold. So if the Poisson tensor is linear in its target space coordinates, then we do get non-abelian gauge symmetries, but standard Yang-Mills type of gauge symmetries. But if the Poisson tensor is more general, then we get some nonlinear gauge symmetries. Okay. Yes?
Are they equivalences? So in other words, can you make redefinition so that it's equivalent to the linear case? Just like there is a Darboux theorem.
Yes. Locally, yes. So locally you can always find Casimir-Darboux coordinates in which the Poisson tensor is not just linear but in fact constant. So like in your lecture, but with the additional possibility of having degeneracy. But you change some global properties by this. So this is not true globally in general. And we must make sure to maintain global properties when we do such transformations, because in some sense, global properties is all there is in these theories, because these theories have no local degrees of freedom. So they are locally trivial, these models. So all the information about these models resides either at the boundary or in the structure of the topology that we're considering. So we are interested in the case when the topology is fixed. So typically we put these models on the disk, but we allow for non-trivial boundary conditions such that we do get boundary excitations. That is going to be the kind of game that we're interested in. And that's, well, if you're familiar with quantum Hall physics, that's very much in the same spirit. So also in quantum Hall physics, the effective theory that describes your system, at least at low energies, is given by the theory that Marc introduced, namely Abele and Chern-Simons. And that is also topologically fit theory. It has no local degrees of freedom, but there can be, and in general there are, non-trivial boundary excitations. So just because you don't have local degrees of freedom doesn't mean that your theory is empty. But that means that you have to be careful with field redefinitions or transformations, or in this case target space diffeomorphisms, because they may not maintain all aspects of the global structure. In particular, what the transformation to Casimir-Darboux coordinates would eliminate, so in Casimir-Darboux coordinates, the Poisson tensor, if it's three-dimensional, would be of this form. Well, the minus sign on the other side. You would lose information about horizons, for instance. So you would transform away horizons. And that's, of course, something that we don't want to do. I mean, we want to make sure that our field redefinition that we do maintain the causal structure of the solutions that we try to describe, and they don't convert black hole solutions into non-black hole solutions. So that's the reason why we can't exploit this. But it's still interesting to see how far you can push this uniformization. And that's an issue that is still not completely resolved. So that's part of the outlook. But yeah, thanks for the question. That's a good point. Okay, and just to see the relation to what we did before. So JT gravity is recovered if we choose the following Poisson tensor, Pij. First of all, it has a three-dimensional target space, so that we have three components in the connection, one corresponding to the spin connection, the other two to the Zweibein. And therefore, we also have the same target space coordinates as before, xa and x. And in light congauge, so x plus and x minus, this Poisson tensor has the following form. So 0 minus x plus x minus, 0 lambda x, 0. And okay, it's antisymmetric, but let me write it down once. So for that choice, you recover the Chekif-Teitelbaum model. And the translation here is that these target space coordinates are the Dilaton field and the Lagrange multipliers for torsion, and the gauge connection is spin connection and Zweibein components. So in other words, the Chekif-Teitelbaum model is a very special case of a Poisson-Sigma model, namely with three-dimensional target space and this Poisson tensor. And I leave it as an exercise to show that this Poisson tensor obeys these two properties. I mean, the first one is obvious, it's manifestly antisymmetric. The second one, well, you have to do one line of calculation, namely this line, but it's straightforward. It's just the usual Jacobi identity of the SL2 Lie algebra. Okay, and from this perspective, it's now clearer to define what we mean by most general two-dimensional Dilaton gravity theory, or how we constructed that theory. There is a notion of consistent deformations that was discussed in great detail in seminal work by Marc and Glenn in the early 90s. So I'm not going to review all aspects of this. If you're interested in details, I refer to the paper by Marc and Glenn, so Barnich and Henneaux. But what it means physically is you allow deformations of your gauge symmetries in such a way that you maintain both the number of field degrees of freedom and the number of gauge degrees of freedom. So you don't change your phase space, your physical phase space, and you also don't change your field degrees of freedom. So the physical phase space maintains the same dimension. And that concept is useful here because it allows us to rephrase the question, what is the most general theory of 2D gravity, by stating it as what is the most general consistent deformation of Chakif-Teitelbaum gravity. So that's what I mean operationally when I say this is the most general theory of gravity. And that was actually answered at the turn of the millennium already. So there's a theorem by Izawa from 1999 who showed that the most general deformation, the most general consistent deformation of a Poisson-Sigma model is a Poisson-Sigma model. So in that sense, Poisson-Sigma models are rigid. You cannot deform them outside the class of Poisson-Sigma models, but you can change the Poisson tensor. So in other words, the most general consistent deformation of JT gravity is a Poisson-Sigma model with the same dimension of the target space, but the Poisson tensor can have a different structure from the JT model. So let me state the theorem. This is due to Izawa. And actually, the proof is not very long, so I was tempted to show it, but I think it takes too much time, and I'll not do it. So, yeah, well, I said it in words, but okay, I'll write it down briefly. So the most general consistent deformation in the sense of Barnich and Henneaux of JT gravity is a Poisson-Sigma model with three-dimensional target space. So that's almost the statement we want, but it's not quite sufficient. The problem is not every Poisson-Sigma model has a gravity interpretation. So that goes back to Bart's question, what about the gauge symmetries? How can we interpret them geometrically? And in particular, what can happen is that you lose the interpretation of one of the components of a connection as a spin connection. So you might lose local Lorentz invariance by deforming to an arbitrary Poisson-Sigma model. So the restriction that you want to impose to make sure that you still have a gravity theory is that you maintain local Lorentz invariance. And of course also diffeomorphisms, but that you will always get. So the non-trivial aspect here is to maintain local Lorentz invariance. And, well, given what I said, you might already anticipate what the result should be. Local Lorentz invariance is always of Lie algebra type. So that means part of the Poisson tensor must maintain the linearity in the target space coordinates. And it turns out that the part that must be maintained is this first row and first column. So if you want to make sure that you have local Lorentz invariance, the only entry of the Poisson tensor that they're allowed to change is this one. And how can you change it? Well, if you don't know anything else, you can just make a generic ansatz of all the target space coordinate. That's clearly the most general thing you could write down. But if you consider this, it turns out this is not a Poisson-Sigma model in general because it doesn't obey the nonlinear Jacobi identities. But it's straightforward to solve them. And the simplification that occurs is that you have to delete this comma here. So the most general solution to the nonlinear Jacobi identities that is consistent with local Lorentz invariance is a function of two arguments, namely of x and of the product x plus x minus. And intuitively, I hope that makes sense because, well, x plus times x minus is a Lorentz scalar, and it's plausible that, to maintain Lorentz invariance, this potential function here should depend only on scalar invariance. And this scalar field is Lorentz invariant by itself, but x plus and x minus would be Lorentz vectors, but the product is again a Lorentz scalar. So that's a geometric way how you can see that this is correct. But you don't have to have this intuition, you just get it if you blindly insert the most general ansatz into the nonlinear Jacobi identities. This is the most general solution. Okay, so this is the answer. This is the most general theory of gravity in the sense that it's the most general consistent deformation of JT gravity that still has a gravity interpretation. And now you can eliminate again this auxiliary fields XA and the spin connection. The calculation is a bit more complicated if this depends on x plus and x minus, but it's still straightforward. It's part of the second exercise, so I'll not do this on the blackboard. But the outcome of this calculation is that you recover precisely the action that I've shown to you. So eliminating XA and the spin connection gives you as the most general two-dimensional action in the second order formulation this action here, x times r minus 2v of x, where this v is the same function as this function. X is the same x as here, and the second argument is then replaced by minus nabla x squared. So that finishes the proof of the claim that this is the most general theory of gravity. So most general in the sense that explained. So the most general consistent deformation of JT gravity that still has a gravity interpretation. Okay. Good. So now we know how to formulate our theory and what's the most general class of theories to consider. And in the remaining time, I want to discuss the asymptotic structure. That's, after all, one of the main themes of Marc's lecture series. And two dimensions are, I think, particularly simple for this purpose, just because, well, there are far less choices that you have. And also you have complete control over the solution space. So you can find solutions to the field equations in closed form for all these models. And that is very helpful when you want to come up with boundary conditions. Because that's usually the hardest part, finding a consistent set of boundary conditions that leads to interesting physics. So that brings me to the fourth point. Let me just abbreviate this point as asymptotic structure. And as a first step, let's solve the equations of motion to get a better understanding how the geometries that we're dealing with look like. So I just write them down. That's again a simple exercise to vary the action with respect to all the fields. So if we vary with respect to a spin connection, we get dx plus x minus e plus minus x plus e minus is equal to 0. If we vary with respect to the Zweibein, we get d plus minus omega x plus minus e plus minus times v is equal to 0. if we vary with respect to x, we get the omega plus epsilon dv by dx is equal to 0. And if we vary with respect to the Lagrange multipliers for torsion, we get d plus minus omega wedge e plus minus epsilon dv dx minus plus is equal to 0. Okay. Now, if you see these equations for the first time, they still look a bit daunting. These are coupled nonlinear first order PDEs. At least they're first order, so this formulation nicely combines the advantages of the Hamiltonian formulation, namely that it's first order, with the advantages of the Lagrangian formulation, namely that you have manifest covariance. But it's still not obvious how to solve them. So let me guide you through this. There are actually two disconnected sectors of solution, and the first one is kind of trivial, but let's discuss it first. So these are so-called constant Dilaton vacua, and they are defined by the property that both x plus and x minus vanish for these solutions. That's the defining property of these solutions. Now, what happens if you make this assumption? In the first equation, you see that a consequence is that dx is equal to 0. So that means x has to be constant. So that's why they are called constant Dilaton vacua, because the dilaton is constant in this sector. Now, if you look at the second equation, since x plus minus vanish, the second term also must vanish, but the Zweibein is not allowed to vanish identically. So therefore, this quantity v must vanish, and that means x cannot be any constant. It has to be a solution of the non-differential equation v of x and 0 is equal to 0. And now you can see that these solutions need not exist. There are some models where no constant Dilaton vacua exists. The simplest is the so-called CGHS model, where v is just a constant, which is non-zero. And then obviously this equation being 0 has no solution. So constant Dilaton vacua may or may not exist. If they exist, you can see from the third equation that the curvature 2 form, so this is curvature, d omega, is just proportional to the volume 2 form times some constant, because dv by dx, well, is some function of x, but since x is constant, this evaluates to some constant, and depending on the sign of the constant, this can be either positive, negative, or 0, and depending on that, you get solutions that are locally de Sitter, anti de Sitter, or flat space. So you get always maximally symmetric solutions. And this sector, first of all, as I said, it's not generic. And second, it's kind of boring, so I'll not focus on it any further. Instead, I consider the linear Dilaton vacua. And since we now assume that not both of these target space coordinates vanish identically, let's assume without loss of generality that x plus is not equal to 0. If x plus happens to be 0 everywhere, but x minus is non-zero, we just replace everywhere the plus by minus index and proceed in the same way. Okay. Now, here's a simple solution algorithm. We introduce a one-form set, which is just defined by the Zweibein component e plus divided by x plus, and that's a well-defined operation because we assume x plus is non-zero. And we can use now the first equation to express E minus in terms of dx and z. So E minus is then just given by dx over x plus x minus times z. And that means the volume form is very simple. It's just given by E minus wedge a plus. So this is dx wedge z. So you can anticipate already that we could use the Dilaton field, the scalar field, as a coordinate. And then we just have to figure out what other coordinate to use. So we would like to integrate this one-form set if possible. The second equation yields an equation for omega. So omega is minus dx plus divided by x plus minus z times v. And for the remainder of my talk, for simplicity, I'll assume that this function v is just a function of x and doesn't depend on the x squared. You can generalize everything that I said, but since it's already 5:10, I don't want to complicate things unnecessarily. So I'll restrict myself to this class of models, which includes the Chakiv-Teitelbaum model and, well, infinitely many other models. And as I said, you can generalize the discussion, but it doesn't add very much to the story here. Okay, so we consider now the last equation here. Also, this last equation here. And we have results for E minus and omega. So the last equation, it's a one-line calculation to show that this simplifies actually to dz is equal to 0. So by making this clever choice of parameterization of our variables, we have converted part of this set of equations to a very simple differential equation, namely the statement that this one from Z is closed. And that means that locally or in a star-shaped region, it's exact. So we just use Poincaré to conclude that locally Z is just d of something, and I call this dv. And that's the other coordinate that we're going to use. So we're using x and v as our coordinates. So we can actually already write down what the solution for the metric is going to be. It's the symmetrized tensor product of E plus and E minus. And, well, E plus is just z times x plus, so it's dv times x plus. And E minus has a term dx over x plus. Oh, sorry, there's a factor 2 missing. So this is 2 dv dx. And then we get another term plus x minus dv squared. So this is our solution for the metric. And, well, it's not quite yet of the desired form, because we don't know what x plus x minus are in terms of the coordinates x and v. So that's the last hurdle we have to take. If we knew what x plus and x minus were in terms of v and x, we would have found our solution for the metric. And therefore, we still need to consider the equations of motion. So we've considered all of them, but, well, all lines of them, but in some lines there were 2 equations. So there's one linear combination of the first 3 equations that we haven't considered yet. And it turns out the useful combination is to multiply the second minus equation with x plus, then add the second plus equation by x minus, and use the first equation. And if you do this, this first 3 equations turn into a simple exact differential equation, namely d of x plus x minus is v of x dx. And that's our desired equation, because now we can integrate and express x plus x minus, as it turns out, just as a function of x. So, okay, I apologize for the notation. This is w, not omega, but it's what has been used in the literature. So w is just is defined as the integral of v. And using this definition, we get finally the result that x plus x minus is w of x minus a constant of motion, which I call m. And this is the only constant of motion of physical relevance here. So the interpretation of this constant of motion is as a mass of our state. And indeed, for concrete models, it turns out to be related to the black hole mass. of our solution.
So maybe I'm a bit lost, but there's also a coordinate v, right?
That's right.
And your d there, dx plus x minus, is a full d, so it's a dx and a dv.
That's right, yes.
So your mass cannot depend on v.
It cannot depend on v, yes, yes. Indeed. So, and that's quite important. So that means that our line element, so I just insert the solution for x plus x minus here. So this is w of x minus n. So that means we have not just obtained all the solutions for all models of two-dimensional dilaton gravity, subject to this assumption here. We have, as a byproduct, also shown a generalized Birkhoff theorem in the sense that there's always a killing vector, which in disadapted coordinates is just dv. So all solutions of all two-dimensional dilaton gravity models have at least one killing vector, which in these coordinates is dv. And this quantity m is a conserved mass that you can use to characterize your solutions. Moreover, this quantity in parentheses is not just some function that appears in some arbitrary gauge. It has a gauge-independent meaning as the norm squared of this killing vector. And therefore, you can give this a nice geometric interpretation, namely the zeros of this quantity. So if w of x minus m vanishes, correspond to killing horizons. So you can use this information to reverse engineer your models. If you want to have a model that for some reason describes black holes with 42 killing horizons, then you have to make sure to choose your function v in such a way that this function w leads to, for instance, a polynomial in x that has 42 zeros. So that's useful information. Yes?
Could you repeat how you separate m from the value of x? Why don't you absorb m in the value of x?
Okay. So there's, of course, an ambiguity in the integration constant. So, I mean, I could convert this into a definite integral. I mean, there's an ambiguity here and there's an integration constant here. I can shift this ambiguity back and forth. I can say, okay, I always integrate this from some reference x naught. And for any choice of x naught, then the value of m will be meaningful. But of course, I can always shift, if you want, the zero value of my mass by any constant amount. I just shift the whole spectrum. But that's an ambiguity we always have. Usually we fix this by choosing the shift in such a way that the mass of m is 0 for the geometry that we consider as our ground state, which typically is empty ADS or empty flat space. But I mean, it's not physically important to fix this ambiguity. It's just shifting the whole spectrum in a state-independent way. But not that this has to be state-independent. This is just some reference value of x naught. So, but there remains one relevant constant of motion in this combination. And that, well, you can check that this is indeed associated with the corresponding boundary charge in concrete models. Okay, but, well, there are some caveats, of course. I have done some gauge fixing here, and as you will learn in later lectures by Marc, it may not be clear if I've used proper or improper gauge transformations to do this. So this is something you have to be aware of. Yes?
The fact that the killing vector is d by dv, is it more than the reflection that only z appeared? Or z is dv, so v up to a constant is z?
Yeah, I mean, the fact that it's a killing vector ultimately comes from the fact that we had this exact differential equation, so that we have this absolutely conserved quantity, so that this constant of motion m did not depend on v, it's just a constant. So therefore, there is no v dependence in our metric at all. But okay, it wasn't obtained by choice. So okay, the choice is that we ended up with this particular gauge, which is Eddington-Finkelstein gauge, and that choice comes from this ansatz here together with this assumption. So geometrically, what's happening is that making this assumption puts you into, say, outgoing Eddington-Finkelstein gauge, which covers usually just half of your manifold. And if you want to cover the other half, you have to make instead the assumption that x minus is not equal to 0. Does that answer your question, or did you want to? Okay. All right. So we have 10 more minutes, and I wanted to end this with a simple example. One of the simplest examples, besides the JT gravity model, is this CGHS model. So let's focus on this. So in that case, v is just a constant, and that means the function w is just linear. So I focus now on an example, namely the CGHS model. So v of x is constant, and therefore w of x is proportional to x. And I call now my radial coordinate r. So instead of dx, I'm going to write dr. And now the whole purpose of finding all the classical solutions for all models is that it gives you a better handle to impose boundary conditions. Imposing boundary conditions, it's like imposing boundary conditions when you try to solve differential equations. And you have to make sure that whatever boundary conditions you are imposing, they are compatible with the actual differential equations that you're trying to solve. So now that we know how generic metrics look like, we can make more better informed answers for the boundary conditions. So I want to consider metrics of the following form: 2dv dr plus some term of order r, which is this function w, plus a term of order 1, and possibly plus subleading terms times dv squared. These are the boundary conditions that I'm considering now. And it's quite crucial to impose boundary conditions on the metric and on your other fields to define your theory. Without this information, you don't have a complete specification of, for instance, what is the state space of your theory. And that's especially important in these topological theories of gravity in lower dimensions. So imposing boundary conditions and choosing them appropriately is at least as important as finding the right bulk action and using an appropriate potential V. So I'll parameterize these terms as follows. So 2dv dr plus, and now I allow myself additional gauge redundancies by allowing a function of v, I call this p of v times r, plus another function of v dv squared. So this is what I operationally mean by order r and order 1. So we're picturing some situation where we're interested in an asymptotic boundary which we assume is located in the limit r to infinity. So we make a Taylor expansion in inverse powers of r, and the leading order term actually diverges linearly in r, and the subleading term is order 1. And this is compatible with the spectrum of the classical solutions that we found here. So these boundary conditions definitely contain all these solutions, but they may contain additional gauge redundant solutions, at least locally gauge redundant solutions, that nevertheless correspond to different physical states. So our assumption here is that delta p can be non-zero and delta t can be non-zero. This is the ansatz by which we start. Okay? Good. And now once you have boundary conditions available, the rest is more or less straightforward technique. So the first thing you can do is you check the asymptotic killing vectors. They're defined as follows. So asymptotic killing vectors are all the vector fields that when they act on a metric, they give either 0 or something that is of the order of the allowed fluctuations of the metric. And that's a key concept in this study of asymptotic symmetries, and I'm sure Marc is also going to introduce this in later lectures. So it's a generalization of the killing equation, which on the right-hand side would have 0. And it's quite a drastic generalization. It may look harmless, but let me show you one immediate consequence. If the right-hand side is 0, then you know that in d dimensions you can have at most d times t plus 1 over 2 independent killing vectors. But if the right-hand side is something like here, order of the allowed fluctuations, then even in 2 dimensions you can have infinitely many asymptotic killing vectors. And what this means geometrically is that we preserve the asymptotic structure of the metric. So if we act with any such asymptotic killing vector on a metric of this type, we get another metric of this type, but in general with different functions p and different functions t. So these asymptotic killing vectors maintain our boundary conditions. Okay. Well, and now we just have to solve this equation. So the first equation is the RR component, and since there is no RR component in the metric, we have to require that this is 0, and that immediately gives you that dr of psi v has to be 0. The second equation is the mixed one, so L psi of g rv. And what is this? Well, grv is non-zero, but there's no fluctuations allowed here. This term always has to be the same, so the right-hand side must also be 0 because this is of the order of the allowed fluctuations and there are no metric fluctuations allowed here. So this also must be 0. And that leads to the following equation. So gr mu, but that has to be v, so grv times dv psi v plus gv mu dr psi mu has to be 0. And if mu here is v, then we get dr psi v, which we know already is 0. So we actually can replace this by gvr. And then we can divide by this, because this is just 1 anyhow. So we get the statement that dv psi v plus dr psi r is equal to 0. So we can solve this for psi r. We get psi r is minus r times dv psi v plus some integration function eta of v. And from the first equation, we know that psi v is just some function epsilon of v. So that means we have already our solution for our asymptotic killing vectors. Psi is epsilon of v dv. And then we have plus, let me write it in this way, plus minus r epsilon prime of v plus eta of v dr. So these are the most general vector fields that preserve metrics of that form. And that means we have 2 functions worth of asymptotic killing vectors. So we have infinitely many killing vectors because there are infinitely many functions epsilon of v and eta of v that you can choose. So that's a very simple example where you find infinite dimensional asymptotic symmetries. Geometrically, what this epsilon generates is diffeomorphisms of the line, or if you compactify the v direction of the circle. So this is diff S1 or diff R. And eta generates something that, you could call radial supertranslations. I'll explain this name in a second. And once you have determined these asymptotic killing vectors, the next step is to determine the algebra. So we're interested in symmetries of our gravity theory. And if we believe the holographic principle is true, then these asymptotic symmetries that we find must be symmetries of the dual field theory, if that exists. So that's why determining these asymptotic symmetries is so crucial, not just for gravity purposes, but also for holographic purposes. So the asymptotic symmetry algebra is the Lie bracket algebra of these asymptotic killing vectors. Well, and given the time, let me just omit doing this calculation on the blackboard. It's elementary. So we just evaluate the Lie bracket between two such killing vectors, and it turns out that you get a single killing vector psi of epsilon 1, 2 and eta 1, 2, where epsilon 1, 2 is epsilon 1, eta 2 prime. Sorry, epsilon 1, epsilon 2 prime minus epsilon 2, epsilon 1 prime, and eta 1, 2 is epsilon 1, eta 2 minus epsilon 2, eta 1 prime. So this is an infinite dimensional symmetry algebra, and in order to get some algebraic intuition what this means, it's often useful to decompose this in modes. So let me write this down. So here I introduce Laurent modes. Ln is defined as psi, where epsilon is non-zero, but it's just given by the coefficient minus u to the m plus 1, and eta is 0. And Mn is defined as psi, where epsilon is 0, and eta is u to the n minus 1. And then when you plug this ansatz or this definition into the Lie bracket algebra, you recover the following infinite dimensional algebra. Ln with Lm gives you n minus m, Ln plus m. Ln with mm gives you minus m, m, n plus m. And the m's commute among themselves. So this is the algebra that we call BMS2. And the geometric interpretation is that this generates diff-S1 or diffeomorphism of the line, and you get the expected width algebra. So this algebra is known as width algebra. And the m's, they commute mutually among themselves. So this is the analog behavior of translation generators. And, well, BMS in the 60s gave generators of this type the name super translations. It has nothing to do with supersymmetry. It's a different super. It just means you have infinitely many of these translation generators. And the commutator between this diff-S1, sometimes also called super rotations, and the super translations gives you, again, a super translation. And, okay, if you have some field theory experience, then you can interpret this as some spin zero field in a conformal field theory. All right. There's more I wanted to say, but my time is up, so I'm not... there's one last point I wanted to make about central extensions, but I don't want to... I do. Okay, good. Yeah, sorry for going over time. Okay, so yeah, one last point. So what I've discussed here is just still pure geometry, in the sense that we have determined a class of geometries by some boundary conditions that we guessed or deduced from the way that the classical solutions look like. And based on this, we determined asymptotic killing vectors that preserve this class of metrics. But we haven't figured out how they change these functions p and t. And for this, I will not have time today, but p and t turn out to characterize the physical state, meaning that different choices for P and T, even though locally they are related by gauge transformations, physically correspond to different states. And therefore it's interesting to find out how these asymptotic symmetries act on the state-dependent functions. So that leads to the canonical realization of the asymptotic symmetries, or the canonical realization of the asymptotic symmetry algebra. And Marc actually famously showed that there can be a central extension when you check the action of the asymptotic symmetries on the state space. And this central extension has important implications for the field theory interpretation, but also for physical observables like correlation functions, entropy, and so on. So it's very important to find out whether or not there is such a central extension, and more generally, it's important to find out how the asymptotic killing vectors act on the state space. So here, concretely, what I mean is how they change P and T. So in order to find this out, we need to consider the last component that we haven't studied yet, namely the change of the VV component. The reason we didn't study this before is because it didn't matter for determining the asymptotic killing vectors, but it does matter for determining how P and T change under the action of the asymptotic killing vector. So this is just what I defined to be delta psi of P and delta psi of T. So any metric is mapped to another metric in the same class, but P and T can change. Okay, and then we just insert into the asymptotic killing vector equation. So there's, maybe let me just write down the result since it's so late. So the result is we get R times epsilon P prime minus epsilon prime P plus 2 epsilon prime P minus 2 epsilon double prime. And then we get an order 1 term plus epsilon T prime plus 2 epsilon prime T plus eta P plus 2 eta prime. So this I obtained just by evaluating the asymptotic killing equation for the VV component and then collecting all terms linear in R and all terms constant in R. So that means we can actually just deduce the transformation of the state-dependent function P and T. And, well, I mean, with this plus 2, I can just delete this term. And you see, if you're familiar with conformal field theories, you should recognize this combination. This is like the behavior of the holomorphic part of a stress tensor in two-dimensional conformal field theory, except that we're missing the remaining term for this to be an infinitesimal Schwarzian derivative. So there's no epsilon triple prime term, meaning that we don't have a Virasoro central extension. And this transformation behavior shows that P transforms like a U1 current in a conformal field theory. So this transformation behavior gives a nice interpretation. And, well, we can skip again a couple of steps, but we can translate this by introducing again modes into a statement about Poisson brackets of the state-dependent functions. And this Poisson bracket algebra is almost the asymptotic killing vector algebra that I've written down. So in particular, the commutation relation between these charges associated with the superrotations is exactly the same as the corresponding Lie bracket algebra between the superrotation generators. So it's again the width algebra. There's no central extension here as a consequence of here not having any epsilon triple prime term. So this gives again the width algebra. Let me skip this for a moment. The last bracket, Pn with Pm, is again 0. So this is again like the super translation part of the asymptotic killing vector algebra. So this is the last line here. And in the middle line, well, okay. I guess I'm skipping 2 steps at once. There is a slight change in the structure constants because we're shifting the spin by 1, but that's incidental. But the more important point, and the last one I want to highlight, is that we do get this central extension. So there's a non-trivial central extension in the algebra, and you can deduce it from this term here. So that's the origin. This 2 epsilon double prime is what gives you this term proportional to n squared. So that's a simple example where you see that the canonical realization of the asymptotic symmetries leads to a central extension. This you need for consistency. So this is actually related to the. So I mean, note that this is the commutator between T and P. So for this to be consistent, to obey the Jacobi identities, you need both this term and this term. But both together form a single co-cycle here. That's this one. And maybe for completeness, let me mention that Pn is n times some, I don't know, mn. And that mn would be the charge associated with these supertranslations. So there's a shift by spin 1. So this was spin 0 supertranslations, and these are now spin 1 supertranslations. Okay, and there's a larger story associated with these central extensions. So these central terms determine numerous properties like thermal entropy, entanglement entropy, correlation functions. So I just want to leave it at that. So in summary, the picture here is that you can take 2-dimensional gravity as a convenient toy model if you have some idea what kind of asymptotic structures you want to describe. So in this case, we get solutions that are locally flat. So we can use this as a model for flat space holography, for instance. But we could have started also with Chakif-Teitelbaum, and then we would have obtained solutions that are locally anti de Sitter, and we can use this for ADS holography. And this is indeed what has happened in the past 6 years or so. The JT model was studied and used to relate it holographically to the SYK model, so a specific condensed matter model consisting of randomly interacting, strongly coupled Majorana fermions. And our hope is that you can do something similar for a larger class of models, including, as a simple example, the CHS model. So stepping back and looking ahead, one of the open questions is how general is holography? So how general does the holographic principle work? The holographic principle, if it's true, relates quantum gravity in d dimensions to quantum field theory in 1 dimension lower. And the best studied and best known implementation of holography is the ADS-CFT correspondence, which relates quantum gravity in anti de Sitter space to conformal field theories in 1 dimension lower. But given all the successes of ADS-CFT, it's interesting to ask how many of these successes are specific features of anti de Sitter space or conformal field theories, and how many of these lessons are general lessons for holography. So statements about correlation functions, entropy, entanglement entropy, how many of those statements depended on specific properties of anti de Sitter space and conformal field theories, and how many of those generalize. And flat space holography is one particular niche to address this question. It's not generic holography, but it's one step away from anti de Sitter space. And this specific 2-dimensional model is a rather concrete model for, or proposal at least, for flat space holography. Okay, so since I'm out of time, I think I want to stop here. Thank you for attention, and if there are further questions, I'm happy to take them.